Dear all, now let's work on some Laplace transform solution of initial value problems. So on the left-hand side, we have a Laplace table where we have functions and their respective Laplace transforms. We can figure out the inverse Laplaces by going from right to left, and the Laplace will be from left to right. So, for example, if we saw 1 over s squared as in the second row, our function would be t for the inverse Laplace. And we can use this table to solve Laplace initial value problems to make our lives much more easier, because most of the time in exams you will be provided one. So I also wanted to add a few important Laplaces for differential equations. So anytime we have a function, the Laplace of that function is going to be capital F of s. The derivative will be s f of s minus f of 0. This f will be a lowercase f. We will have, for double f double prime, we will have s squared capital F of s minus f0 and minus f prime of 0. And when we're dealing with initial value problems, most of the time you will be all the time you're going to be provided with f0 and f prime of 0. So that's just going to make our lives much more easier. We're going to take the Laplace of the left-hand side for an equation, take the Laplace of the right-hand side, plug the initial values in, and then sort of figure out what capital F of s is actually equal to in terms of s. And since the inverse Laplace of f of s is going to be f of t, we're going to be able to figure out what f of t is. So here's a really nice problem. First of all, if I hope you can solve this problem, so please pause this video and try it on your own. Now let's start solving this Laplace transform problem. So y double prime plus 3y prime plus 2y equals to 4. Okay, well, this is a non-homogeneous differential equation. We could solve this using variation of parameters, undetermined coefficients. All of these methods would work. That's correct. You don't need Laplace to solve this, but for the sake of argument and the sake of learning, we're gonna use Laplace. So the first thing we want to start is taking the Laplace of both sides. And as you can see, f of t is capital F of s, f double prime is this, and we can literally just use these things. Well, you should kind of memorize what they are, especially for these functions, because they're going to come up a lot if you're solving Laplace differential equations. So we're going to have s squared y of s minus s y of 0. Notice how I changed the variable from f to t, y, because now we're dealing with f is not defined in this problem, so we want to have something that's defined, and y minus y of 0 plus, now we're going to say, y prime of 0, and we're going to say plus 3sy of s, 3sy of s, and minus y of 0, 3y of 0. And finally, we're going to have plus 2 capital Y of s. Okay, this is the Laplace of left-hand side. Okay, let me write this a little bit smaller so we can fit this right in. Okay, the Laplace of the right-hand side is going to be, so what is the Laplace of a constant? You should definitely know the simple ones like this one. The Laplace of a constant is 1 over s. Okay, I mean, if in the first time it might be a little hard to memorize all of these, but please do try to memorize them. At least some of them you should know. So we're gonna write 4 as in 4 times 1, and the Laplace of 1 is gonna be 1 over s. And notice Laplace is actually an integral, right? Laplace is defined as an integral. So we can actually pull this 4 out like a constant. So in the end, what we will have is gonna be 4 over s. Okay? Well, now we have a really messy equation. So first of all, what you want to do is we're going to go ahead and know what our constants are. So we know that y0 is 1 and y prime of 0 is 0. So y prime is just going to get canceled right away. Where I'm going to plug y0 equals to 1. So we're going to say s squared y of s minus s plus 3sy of s minus 3 plus 2y of s equals to 4 over s. Okay, now guys, listen. Our goal is to leave y of s alone. We are trying to solve for y of s. And the reason why we're doing it is because if we have y of s, okay, we can literally inverse Laplace it to get y of t. Okay, I mean basically solving differential equations is trying to understand what y is equal to. All of the time we're trying to solve for y. So when you want to solve a differential equation, you just want to find y. And now we're going to find y of s, and inverse Laplacing y of s is going to give us y of t, which is a solution of the differential equation. So now we're going to do a little bit of algebra. I just want to get rid of all of that messiness. So I'm going to say y of s times, I'm going to factor a y of s outside, s squared plus 3s plus 2. And we can put these guys next to each other. So we're going to say minus s minus 3 equals to 4 over s. And then we're going to go another step. We're going to say y of s times s squared plus 3s plus 2. Notice how this is a really nice factorable polynomial. So that's actually a hint that we're going to use partial fraction decomposition. So we're going to have 4 over s plus, s plus 3. I want to leave this like that because we can make it work. Yeah. And then in order to solve for y of s, we're going to say y of s is equal to 4 over, I'm going to factor this out. So the factorization of this is going to be s plus 1 and s plus 2. So we're going to have s times s plus 1 times s plus 2. Okay, plus, and we're going to have s plus 3 over s plus 1 and s plus 2, like that. Okay. I mean, some professors might choose to write this as s plus 2 plus 1 and kind of get this 1 in a different fraction and cancel one of this out to make it easier. I think actually that's a good idea, because if we do that, we're gonna have one of the elements of our answer right away. So I'm actually kind of tempted to do it. Okay, so what we're gonna do is, first of all, I want to start with this guy. We can say that s plus 2 plus 1 is equal to s plus 3, and having the same denominator, obviously. But I'm gonna carry this 1 in a different denominator, so we're gonna have like this. Okay. Okay, and s plus 2 is going to be s plus 1 divided by s plus 2, the same denominator. So if we can add these fractions, we would get the same thing. And we could just cancel this out, and one of our elements will be 1 over s plus 1. And, 1 over s plus 1 should ring a bell. It's going to be e to the minus t when you take the inverse Laplace. So let's note that one part of our answer is e to the minus t. And now if we want to do partial fractions for this little fraction, that's going to be really easy. So 1 over s plus 1 times s plus 2. Okay. You know what? Just so you don't get confused, I'm gonna call this a triangle. This guy can be a rectangle, and this can be a circle, and circle plus, square or rectangle or whatever, plus triangle is gonna be our solution. So we got triangle so far. So now we're trying to find for square. Okay, so equals to a over s plus 1 plus b over s plus 2. These are just the partial fraction decomposition. And a times s plus 2 plus b times s plus 1 will give us 1, because if you expand this by s plus 2 and expand this with s plus 1, we're going to have the same denominator. We can just cancel that out and get this equation. So we know that as plus 2a plus bs plus b will be equal to 1. This gives us a system of equations where a plus b equals to 0 because we have no s terms, and 2a plus b will be equal to 1. And we know that this equation implies that a equals to negative b. So when we see a, we can plug negative b, and we're going to have negative b equals to 1. This means b is going to be equal to 1. A is going to be equal to negative 1. And is that right? Let's, I think, no, b is negative 1, and a is going to be 1. Yes. So we found that a is 1, and b is negative 1, okay? A, negative 1 and 1. So now we found the partial fraction. It's going to be 1 over s plus 1 and minus 1 over s plus 2. Well, this is going to be e to the minus t, and this is going to be negative because of the symbol, e to the minus t. Okay, so we are able to find, we were able to find the triangle as well, and we had I'm sorry, we found the rectangle, and we had triangle equals to e to the minus t. So e to the minus t plus e to the minus t is going to be 2e to the minus t, and we're going to add that to minus e to the minus 2t. So so far this is going to be triangle plus rectangle. Now all what we need to do is to find circle. So we're going to go back here. I'm going to copy this little fraction. We're going to make partial fractions again and solve this little fraction. And then once we do it and inverse Laplace it, we're going to add it to triangle plus rectangle, this little thing right here. And then once we do that, that's going to be our solution for y of t, in terms of t, yeah. So first, so what we can do is, make a little partial fraction, a over s plus b over s plus 1 plus c over s plus 2. Okay, and now all we need to do is find the constants. Once we find the constants, we know that this is the inverse Laplace of 1 over s is going to be a constant number. This is going to be e to the negative t, but multiplied with some kind of constant, and c times e to the minus 2t. So we already have a basic answer for here without the constant. So now I'm going to go ahead and do partial fractions here. So we're going to expand everything. So we're going to have a times s plus 1 times s plus 2 plus bs, okay, I'm multiplying the bs, times s plus 2 plus cs times s plus 1. And this all must be equal to 4. Okay, so we're going to get a few equations here. As squared, I'm going to kind of multiply this. So we're going to have s squared plus 3s plus 2. So we're going to have as squared plus 3as plus 2a. And we're going to have bs squared plus 2bs plus cs squared plus cs equals to 4. Okay? And a plus b plus c must be equal to 0. The reason is because we don't have an s squared term. And we have as squared, bs squared, and cs squared. The like terms are always going to be combined, so we're going to know that a plus b plus c is 0. So we can kind of cancel out this little thing. We're going to have 3a plus 2b plus c equals to 0. This is another equation because we don't have any s terms, and we have 3as, 2bs, and cs, so they're also going to be canceling each other out, and we know that 2a is equal to 4, implying that a must be equal to 2. Well, that's really nice that they gave us a right away. Okay, And now all we have to do is kind of just work with this two system equation, right? We're gonna just plug A, okay? If you have two variables, guys, you need two equations to solve it. If you have three variables, you need three equations to solve it. Well, in this case, thankfully, we're getting rid of A, which is why we're gonna have only two variables and two equations, which means it's a solvable equation. So B plus C is gonna be equal to -2 if we plug A and throw it away to the other right-hand side. Likewise, 2b plus c will be equal to -6, and we have these two equations. Well, we can subtract equation number 1 from equation number 2. Okay, if we do that subtraction, we're going to say b is equal to, and -6 minus -2 is going to be -4. Therefore, c is going to be equal to 2. Okay, and you can kind of check that work by plugging these guys right back in there. But now that we were able to find our coefficients, we can go back up, okay, copy everything here, okay, go back down, paste all of this thing here, and plug our coefficients back in. So a was going to be equal to 2, so we're going to write a little a 2 for a. B is going to be equal to -4, and C is going to be equal to -6. And this is just going to be 2, because 2 over S is the inverse Laplace of 2, because 1 over S is just going to be 1. You can use a table for your reference. So this inverse Laplace is going to be 2. -4 is our coefficient, and times e to the minus t. Okay, because this is also like the inverse of e to the minus t, and -6 is our coefficient, e to the minus 2t. And now we have our circle, and now what we want to do is add that circle back up to the triangle plus the rectangle or square. Every square is a rectangle, guys, so there's no confusion there. Of course, they're a little different, but it's okay. We want to add this to this thing over here, so we're gonna have 2 minus 4e to the minus t minus 6e to the minus 2t plus 2e to the minus t minus e to the minus 2t is our final result. Not final result, we need to simplify this. So when we simplify, we can see that for e to the minus t and e to the minus t, they're gonna work together. So we're gonna have minus 2e to the minus t, and -6e to the minus 2t minus e to the minus 2t will be equal to -7e to the minus 2t. And this, guys, right here is our solution as a function of y. So basically, it's actually, I know it might look a little confusing because we did a lot of work, but most of this work is just simple algebra, guys. Laplace requires a lot of algebra, which is why it's kind of tedious. But it's not hard. It's definitely a very simple idea. The idea is, I want to go over it briefly. We're going to write everything in terms of their Laplaces, okay? Imagine this. We have a function, okay? You want to Laplace this function, and then inverse Laplace the function, okay? But the thing is, we don't have this function on its own. We have like function times function, okay? Let's say function times function, or, you know, a g function, okay? And we're gonna like do some algebra, leave y of s alone, and then get what we want. And then once we have what we want, we're gonna do the inverse Laplace to figure out what it is. So Laplace is basically just this, guys. So we're gonna we wrote this equation, we found y of s as a factor, and then we did a little bit algebra and said y of s is equal to these two fractions, okay? And then I used a clever trick. I said, hey, I call this circle, by the way, don't get this wrong by 0, this is a circle, okay? This is a circle. I said, hey, we know there's an s plus 2 here. I want to actually cancel this s plus 2 so I can make my life a little more easier. So I went ahead and wrote this as s plus 2 plus 1, and you can use algebra to separate these two fractions. And I said s plus 2 over this polynomial plus 1 over this polynomial will be equal to s plus 3 over this polynomial. Knowing this, I was able to kind of cancel this guy out and get 1 over s plus 1. And this is just obvious that it's going to be e to the minus t. Over here, this is a partial fraction, so we had to do this partial fraction. Likewise, the circle fraction is also a partial fraction. So we did two partial fractions for two different fractions. And for the first guy, we got some coefficients. We did a little algebra, and we got this little thing. We got the equivalent of this fraction is going to be 1 over s plus 1 minus s plus 2. And then after doing this, we were able to inverse Laplace and get this little function of t. And for the same way we did that with this fraction, and we got three fractions. So we had three variables we had to work with, and we were able to find them pretty easily. And finally, we added all of these Laplaces together, and we got our final solution for y of t.